In this video, I'm going to go over one of the major uses of RDS Analyst and one of the major uses of respondent-driven sampling in general, which is to find frequency estimates, the percentage of the target population that is described by some characteristic. So a common example is to find the infection rate, or in other words, the percentage of the population that suffers from a certain disease. So there are two parts to this in RDS Analyst. One is the sample frequencies. So of the sample population, what percentage of them suffer from a disease, for example. And then also the population frequencies, which would try to estimate that feature of the whole target population using the sample data. So just quickly, I'll show you the output, and then we'll show how to create this output. This is the sample frequency table. So looking at my data set for a moment, I've used this data set in other videos, so you might be familiar with it, but it's the faux data set, which you can load through packages and data example faux. We have ID, recruiter ID, so this is recruiter ID formatted data. This is how we track the respondents and who brought them into the sample. And then we're going to use X as our characteristic of interest. So X just has red and blue, but X could be anything in general. It could be diseased or not diseased, or lives in a certain area or doesn't. So going back to the sample frequency table, we have a characteristic, in this case X, the number of cases of each type in our sample, and then percentages, and that's pretty standard. So we had 389 cases in total, no missing data in this variable, and that's our case summary. Then we go down. Using a more involved computation, we have the population frequency estimates. So the point estimates is pretty similar actually to the sample estimates, but we also here have a confidence interval for this point estimate and for red as well. And also reported as a design effect, which is the multiplier for the size of the sample necessary to get the same power as if you were using a simple random sample. So in this case, a simple random sample of 100 is equivalent to an RDS sample of 130. So we need a bigger sample. And then lastly, let me just expand this. Lastly, we have standard error and sample size that was used in the calculation. Again, no missing data, so this is our full sample. So this is the output of the dialog. Now let's go back and see how to create this output. The sample frequency estimate is pretty straightforward. Just go to sample frequencies, pick your data set, your variable of interest, X in this case, and press OK, and then you'll get that standard table. The population frequency estimate has more features to set in the dialog. So up here we have the settings the same as it was for the sample frequencies. We'll also keep the confidence interval at the default of 0.95, 0.99 is another common one. Subset expression will just restrict the data from the sample that you'll be using to make your estimates. A common reason to use a subset would be if you wanted to exclude the first waves of sampling, if they were biased, which they might be because it's a convenient sample, so you could do something like wave greater than 1. One thing to notice, if you use a subset expression, you can't get a diagnostic plot. And now we'll talk about this bootstraps and these weights. So the methods used here to calculate the intervals, the confidence intervals, involve generating new samples, sort of quasi-samples from the data. And so the number of bootstraps is the number of those generated samples. Probably the most confusing part of this dialog is this weights panel. If you haven't seen this in other dialogs or anywhere else in the software, you'll be wondering what's the difference between these weights and which one should I use. So I'm going to go back for a moment to another one of the help pages. From the main RDS Analyst help page, click on Compute Sampling Weights, and you'll come to this page. There's actually a separate dialog if you just want to compute weights to store in your data, but the description here is relevant to the frequency dialog, the population frequency dialog. So now with this open, let's go through these weight types. The first is Giles SS, or sequential sampler, sometimes subsequent sampler, it's called. And This is recommended when the sample is a significant fraction of the target population, which is common when using RDS. Both Giles and RDS2 base their estimates on reported network sizes and inclusion probabilities for individuals in the sample. So they follow along with more classic survey sampling techniques like Horvitz-Thompson estimators. On the other hand, RDS1 uses a Markov process to make its estimates, and in terms of the data, it's based on the number of connections between, if your variable of interest is X, those who in this case are red and those who are blue. And it tries to get an equilibrium estimate of in the population, the percentage red, percentage blue, based on those connections. RDS1 DS is just a slight variation on RDS1, where you assume that the Markov process used in the estimate is reversible. In practice, it probably won't affect the outcome. Arithmetic mean is essentially a lack of weighting. All of the sample is weighted equally. For RDS1 and RDS2 estimates, a population size is not required, although you can enter one if you have an estimate. Another interesting thing to note is because Giles and RDS2 are based on reported network sizes, any individual with the same network size in the population is given the same weight, whereas because RDS1 estimators are based on connections over the variable of interest, in this case anyone with red would have the same weight as another person with red, whereas anyone and all blues have the same weight as all blues. Now let's go back to the population frequency estimates. So what are the diagnostic plots? Well, the first one, the convergence plot, is going to tell you whether your estimates, your frequency estimates, are converging to a certain point or still fluctuating. If they're still fluctuating, it probably indicates that you need a larger sample or additional waves of sampling. But hopefully it will stabilize as the waves of sampling increase. The bottleneck plot essentially tells you whether your choice of seeds for the sample is going to strongly affect your results. In the help page for frequency estimates or population prevalence, there are examples of convergence plots and bottleneck plots. Ideally, in a convergence plot, you want to see something like this where the estimate is leveling off as the number of observations increases. And hopefully you don't see something like this, which would indicate you want to do more sampling so that you get a stable estimate. You have an example of bottleneck plots, the first where the choice of seeds did not strongly impact the frequency estimates, and another where it did. Here you can see that regardless of the seed or the colored line in the plot, the estimate is heading towards the same value, approximately 50%. This plot was actually created using a random variable where we know the true value is 50%, but they're all heading in the right direction. Meanwhile, this plot, depending on the seed, the lines end up in very different places. If that's true, then your choice of sample is going to strongly affect your results. Going back to my dialog, I'm now going to use both of these plots, select Giles. I have an estimated population size of 1,000, which I know is good for this data set. And I'm going to let the simulations per iteration, just a sampling preference, stay at its default of 1,000. So this is the output for the Giles estimator. It took a couple minutes to calculate. The point estimates are very similar to what they were for the arithmetic mean calculation and for the sample frequency calculation. But again, we get a confidence interval on those values from using Giles' method, as well as a new design effect, standard error, and our sample size stays the same because we have no missing data here. I can also take a look at the convergence plot, which shows that my estimate is stabilizing. Now I can go back and compare that estimate with the RDS2 estimate. And since I only have one seed, I don't need to look at the bottleneck plot, so I'll run. This is generally going to be a faster calculation, but in this case the point estimates are only different by really 1 percentage point. The confidence interval is also pretty similar, although the design effect is significantly larger. And again, the convergence plot looks the same. Lastly, I'll compare with an RDS1 estimate. And again, the estimate is similar. Confidence intervals are similar, and the design effect is even slightly larger. This won't always be the case that all of the estimators give such similar results, and it might be worth comparing for your data set. Okay, that's all for now on the population and sample frequency estimates. But again, you can go to the RDS Analyst help pages on both of these dialogues and get more information. Thank you.